Hi, we use the phrase angles of elevation and depression when working with angles and lengths in real life situations. In this section, you will not be given right angle triangles to work with, so you will need to draw them based on the information given to you. Before we look at how we construct these triangles, we have to look at exactly what the phrase angles of elevation and depression actually means. Imagine you have a diver swimming in the ocean. There is a ship sailing on the water, and directly below it is a whale lying on the ocean floor. The ship is traveling across the water in a straight horizontal line. The whale is lying on the ocean floor. Let's assume the ocean floor is flat. This means that we can draw another horizontal line down here for the ocean floor, parallel to the top of the water where the ship is. If the diver swims straight ahead, he or she will swim in a horizontal direction, parallel to the top of the ocean and the floor. The whale is directly beneath the ship, so you can draw a vertical line over here. Now we have 90-degree angles because the path of the ship on the surface, the direction of the diver, and the ocean floor are all perfectly horizontal, and the line between the ship and the whale, directly beneath it, is perfectly vertical. Now we can look at angles of elevation and depression. The word elevation means to rise up or move upward. So if the diver were to begin swimming toward the ship, they would be swimming in an upward path. So you can draw a line from the diver to the ship on the surface of the ocean. To find the angle of elevation, we start at the horizontal, the original path of the diver, and we draw an angle up to the line we have just drawn. This angle is the angle of elevation. But what if the diver decides to swim down to the whale? Let's draw a line from the diver to the whale. The word depression means to move downwards. So to find the angle of depression, we start at the horizontal line and move toward the line down to the whale. This is our angle of depression. The angle of elevation or depression will be different depending on the point of view you are working with. Always remember that when you look up, it is an angle of elevation, and when you look down, it is an angle of depression. So now let's imagine the whale looks up to the diver. What is the angle of elevation? Let's draw a line from the whale to the diver. And to find this angle, we start at the horizontal line of the ocean floor and move up to the line we have just drawn. This is our angle of elevation. Now let's say the captain is standing on the ship, looking at the diver. He is looking downwards toward the diver. So let's draw a line from the ocean surface to the diver. The captain is looking down, so we are looking for an angle of depression. To find this angle, we start at the horizontal line and draw an angle to the line going down to the diver. As you can see, we are working with 90-degree angles, so we can use Pythagoras and trigonometry to find not only the angles of elevation and depression, but the distances between the different elements as well. Let's look at some examples of how we can work with angles of elevation and depression. A ladder 25 meters long is resting against a wall. The angle of elevation between the bottom of the ladder and the wall is 37 degrees. How far is the wall from the base of the ladder? Let's start by drawing a straight horizontal line for the ground. Then we can draw a vertical line for the wall. The ladder is leaning against the wall, so let's draw a ladder over here. Now the floor is horizontal and the wall is vertical, which means the wall and floor are at a 90-degree angle to each other. The question tells us that the ladder is 25 meters long, so let's put 25 on our diagram over here. The angle of elevation between the bottom of the ladder and the wall is 37 degrees. So we can draw an angle from the horizontal floor to the ladder and write in 37 degrees. Now we have a right angle triangle. The hypotenuse is always directly across from the 90-degree angle. So the ladder is the hypotenuse of this triangle. we are working with a 37-degree angle. So this is our opposite side, and this is our adjacent side. The question wants us to find the length of the base of the ladder from the wall. So we need to find the length of the adjacent side of the triangle. Let's make a note of our trigonometric ratios. From SOHCAHTOA, we know that sine theta is equal to opposite over hypotenuse. Cos theta is equal to the adjacent over the hypotenuse. And tan theta is equal to the opposite over the adjacent side. Now we have the value of the hypotenuse, and we need to find the length of the adjacent side. So we need a trigonometric ratio that uses both the hypotenuse and the adjacent, and cos uses both of these. So now we can say cos, our angle, 37 degrees, is equal to the adjacent side, let's call it A, over the value of the hypotenuse, which is 25 meters. To get A by itself, let's multiply both sides by 25, and we get 25 multiplied by cos 37 degrees is equal to A. Now we can take our calculator, and we say 25 multiplied by cos 37 degrees, close the bracket, is equal to 19,965. Let's round off to 2 decimal places, and we see the adjacent side A is equal to 19,97 meters. Let's do another example. Matthew flies a kite on a 17-meter string at an elevation of 63 degrees. Part A asks, what is the height h of the kite above the ground? And B, if Matthew's friend Stephen stands directly below the kite, calculate the distance d between the two frames. Before we start with part A, let's look at the information we have been given and draw a diagram. Let's start with the ground that Matthew is standing on. He's flying a kite, so let's draw a line up to the kite. Next, we can draw a vertical line from the kite back down to the ground. The vertical line is perpendicular to the ground, which means that here we have a 90-degree angle. The question tells us the string of Matthew's kite is 17 meters long. So let's put 17 into our diagram over here. The angle of elevation to the kite is 63 degrees. Now, please don't overthink this. You do not need to worry about how tall Matthew is. We measure the angle of elevation from the ground. So in this case, this is our angle of elevation, and we can fill in 63 degrees. Now we can look at what the question is asking. What is the height h of the kite above the ground? We need to find the length of the vertical line from the kite to the ground. Let's call it h. But please don't let this confuse you. In our past videos, we have noted the hypotenuse of a triangle with the letter h, but it does not mean that this side is the hypotenuse. In this case, h shows the height of the kite. To make it clearer, let's find the hypotenuse of the triangle. The hypotenuse is always directly across from the 90-degree angle. So in this case, this is our hypotenuse. We are working with an angle of 63 degrees. So this is our opposite side, and this is the adjacent side. Now we have an angle, the length of the hypotenuse, and we need to find the length of the opposite side of the triangle. Sine uses both the opposite and the hypotenuse. So now we can say sine, our angle, 63 degrees, is equal to the height of the kite, let's call it h, over the hypotenuse, which is 17 meters. To get h by itself, let's multiply both sides by 17, and we get 17 multiplied by sine 63 degrees is equal to h. And now we can take our calculator, and we say 17 multiplied by sine 63 degrees, close the bracket, is equal to 15,147. Let's round off to 2 decimal places, and we see that h is equal to 15,15 meters. Now we can make some space and put the length of h into the diagram. Let's move on to part B. If Matthew's friend Stephen stands directly below the kite, calculate the distance d between the two frames. If Stephen is standing directly below the kite, he is standing over here where the vertical line meets the horizontal. He is on one side of the adjacent side of the triangle and Matthew is on the other. So to find the distance between them, all we have to do is find the length of the adjacent side of the triangle. Now we have an angle and two sides, so we can use trigonometry or Pythagoras to find the length of the unknown side. But remember, the simplest method is always easiest. So in this case, we're going to use trigonometry. The hypotenuse is 17 meters long and our other side is 15,5 meters. Let's use the hypotenuse because it has a simpler value. We need to find the adjacent side. So we need a ratio that uses both the adjacent and the hypotenuse. And cos uses both of these. So now we can say cos, our angle, 63 degrees, is equal to the adjacent side, which is the distance d, over the hypotenuse, which is 17. Now to make d the subject of the equation, we multiply both sides by 17. And we get 17 multiplied by cos 63 degrees is equal to d. And now we take our calculator and we say 17 multiplied by cos 63 degrees, close the bracket, is equal to 7,717. Let's round off to 2 decimal places. And we see the distance d is equal to 7,72 meters. Let's do another example. David and Charlie stand facing each other at the opposite sides of a 10-meter flagpole AB. The angle of elevation from David to the top of the flagpole is 50 degrees, and the angle of elevation from Charlie is 33 degrees. Calculate the distance DC between David and Charlie. Let's start by drawing the ground that David and Charlie are standing on. Let's say that David is standing on this side and Charlie is standing on this side. Between them is a flagpole. So let's draw a vertical line and call it AB. The question tells us the pole is 10 meters long. So let's make a note of this on our diagram. The flagpole is perpendicular to the ground. So we can draw a 90-degree angle over here and another one on this side. The question tells us the angle of elevation from David to the top of the flagpole is 50 degrees. So let's draw a line from David's feet to the top of the pole. And we can draw in our angle of elevation and note its size as 50 degrees. The question also tells us the angle of elevation from Charlie to the top of the flagpole is 33 degrees. So let's draw a line from Charlie's feet to the top of the flagpole, draw on our angle, and note the size as 33 degrees. Now we need to find the length of the distance DC between David and Charlie. But in triangle ADC, we don't have a right angle, nor do we have enough information to find this distance. So we need to look at what we do have. We can see in our diagram the length of DC is the length of DB plus the length of BC. So let's make a note of this up here. Now DB is one side of the right angle triangle ADB, and BC is one side of the right angle triangle ABC. And we can use trigonometry to find both of these sides. Let's start with triangle ADB, and we can mark it in red. In this triangle, side AD is the hypotenuse because it is directly opposite the 90-degree angle. We are working with an angle of 50 degrees, so side AB is directly opposite the angle and DB is adjacent to it. We can now see the opposite side is 10 meters long and we need to find the adjacent side. We need a ratio that uses the opposite and adjacent sides, and tan uses both of these. So now we can say tan, our angle, 50 degrees, is equal to the length of the opposite side, 10, over the adjacent side, which we can call dB. Now we need to make dB the subject of the equation. So let's start by moving it out of the denominator of the fraction. So let's multiply both sides by dB, and we get dB multiplied by tan 50 degrees is equal to 10. Now to get dB by itself, we divide both sides by tan 50 degrees, and we get dB is equal to 10 over tan 50 degrees. And now we can take our calculator, and we say 10 divided by tan 50 degrees, close our bracket, is equal to 8,39. We can make a note of this over here. It is the length of dB. Let's tidy up our triangle, make it blue again, and make a note of the length of dB over here. Now we can tidy this up and look for the length of BC. BC is a side in triangle ABC. So let's make this triangle red. In this triangle, AC is the hypotenuse. AB is the side opposite the angle of 33 degrees, and BC is the adjacent side. Again, we have the length of the opposite side, and we need to find the length of the adjacent side. So once again, we can use tan, and we can say tan, our angle, 33 degrees, is equal to the length of the opposite side, 10, over the adjacent side, which in this case is BC. Now let's move BC out of the denominator of the fraction, and we get BC multiplied by tan 33 degrees is equal to 10. To get BC by itself, let's divide both sides by tan 33 degrees, and we get BC is equal to 10 divided by tan 33 degrees. Let's take our calculator, and we say 10 divided by tan 33 degrees, close the bracket, is equal to 15,398. Let's round off to 2 decimal places, and we see that BC is equal to 15,4. Let's tidy this up, make our triangle blue again, and make a note of the length of BC on our diagram over here. Now we have the lengths of DB and BC, so we can use this to find the length of DC. So we say DB, which is 8,39 meters, plus BC, 15,4 meters, is equal to 23,79 meters. This is the length of DC. Let's do one more example. A lighthouse keeper measures the angle of depression from the observation point at the top of a lighthouse to the foot of a man as 34 degrees. The lighthouse keeper knows the height of the lighthouse is 15 meters. How far away from the lighthouse is the man standing? Let's start by drawing a horizontal line for the ground the lighthouse is built on. We can draw a vertical line for the lighthouse. The lighthouse is perpendicular to the ground, so we can put a 90-degree angle in over here. Now, the question tells us we are working with an angle of depression, but before we can consider this angle, we need to draw a horizontal line from the top of the lighthouse parallel to the ground. This line is parallel to the ground, which means it is also perpendicular to the line we have drawn for the lighthouse. So we can put another 90-degree angle in over here. Now we can draw a line from the top of the lighthouse down to the man standing on the ground. The angle of depression is 34 degrees. So let's draw an angle from the horizontal line, and we can fill in our angle of 34 degrees. The question tells us the lighthouse is 15 meters high. So let's make a note of this on our diagram as well. Now we have a right angle triangle. I'm going to make it red. The hypotenuse is directly across from the right angle, but the angle of depression is outside of the triangle. So at the moment, we don't know where our opposite or adjacent sides lie, and we don't have enough information to use trigonometry. So what do we know? The vertical line that we have drawn for the lighthouse is at a 90-degree angle to the horizontal line from the observation point. We know that angle of depression is 34 degrees. So if we take 90 degrees and subtract the angle of depression, it will leave us with the internal angle at the top of the triangle. So we can say 90 minus the angle of depression, 34 degrees, and we get 56 degrees. Now we can draw our internal angle into the top of the triangle. Let's make it green. And we can fill in 56 degrees. Now we have an angle to work with, which means that this is now our opposite side, and this is our adjacent side. We need to find the distance between the bottom of the lighthouse and the man. So we need to find the length of the opposite side of the triangle. We have the length of the adjacent side. So we need a ratio that uses both the opposite and the adjacent. And tan uses both of these. So now we can say tan, our angle, 56 degrees, is equal to the opposite side, let's call it O, over the adjacent side, which is 15 meters. Now to get O by itself, we have to multiply both sides by 15, and we get 15 multiplied by tan 56 degrees is equal to O. Now we can take our calculator and we say 15 multiplied by tan 56 degrees, close the bracket, is equal to 22,238. Let's round off to 2 decimal places, and we see the distance is 22,24 meters. And we have now completed this question.